So today we will take up the topic of simple harmonic motion. As you know, in nature things change with time. Dynamical variables change as a function of time, and very broadly speaking you can distinguish two different kinds of change. One which is completely irregular in some sense, unpredictable, and the second one shows a lot of regularity. In particular, very often you see periodicity. Things come back to their starting point after some time and the cycle is repeated on and on. So this periodic motion is what we are going to talk about today, and simple harmonic motion is the fundamental paradigm of periodic motion. So it is so important and appears in so many places, and it is so common that it is worth paying some attention to and understanding in some detail. It is the very model of periodic motion, and all periodic motion in some sense is built upon making simple harmonic motion more and more complicated as one goes along. So it is the fundamental, let me write this down, it is the fundamental model of periodic or oscillatory motion. So let us begin to analyze this simple harmonic motion, and let us do this by starting with what we already know, namely the mechanics or the motion of a particle moving in one dimension, say the x axis, and let us say the particle has mass m, and I write Newton's equation for it. So I start by writing mass times the acceleration equal to the force on the particle, and the particle moves on the x direction, on the x axis, in a manner prescribed by this force here, and in general this force could be a function of where the particle is. So let us say it is f of x. Of course you could look at a more complicated situation where this is also a function of t explicitly. I could shake the particle by hand as a function of time. That leads to a different kind of motion. We will not get into that. It is called forcing motion, and this we will study a little later, but for the moment we look at cases where f is independent of t explicitly but depends on it implicitly, because x depends on t. X will change as a function of time, and the task is to solve this equation in some sense. Now we have seen that when the force is conservative, I do not put vector symbols because we are in one dimension, and we will take the convention that when f is positive it acts to the right, when it is negative it acts to the left. Okay. And here is the origin. Okay. Then in the case when f of x, if it is a conservative force, implies that f of x can actually be written as minus the derivative of a certain quantity called the potential v of x. So let us consider the case where f is a conservative force. Then this becomes equal to minus dvx over dx, and the task is to integrate this equation. But this is not such a trivial task, because this is a second derivative. Had it been a first derivative I could have just written the integral down, but it is a second derivative, and we need to find two constants of the motion in some sense when you integrate it twice. But there is a simple way of seeing what a constant of the motion in this problem is, as follows: multiply both sides of this equation in general by x dot. Just manipulate by multiplying by x dot on both sides. And then you have m dx over dt, that is x dot, and then d2x over dt2. This is equal to minus dvx over dx times dx over dt. Here. But we recognize that the left hand side is the derivative of dx over dt whole squared apart from a factor half, because this thing here is the same as saying d over dt of 1/2 m dx over dt whole squared. If you differentiate that, then you get a factor 2 first, which cancels against this, the m comes out, it is a constant, and then you have twice dx over dt times the derivative of dx over dt, which is the second derivative here. So the left hand side is the time derivative of this combination here. But the right hand side is equal to minus d over dt v of x. It is the time derivative of this function of x where x is a function of t. That is the chain rule for finding the derivative of v of x. Function of a function, you differentiate first the function with respect to its argument and differentiate the argument with respect to time. But bringing this to the left hand side, it says d over dt 1/2 m. Let me put a dot just for convenience, overhead dot to denote the time derivative, that is a standard notation, x dot squared or the velocity squared plus v of x equal to 0. So it says no matter how x changes with time, this particular combination of x and x dot does not change with time, this combination here, right? Which will of course immediately imply that this combination 1/2 m x dot squared plus v of x equal to a constant of the motion, because the derivative of a constant is 0 by definition. Okay. And let us call this constant E, say. And I have a reason for calling it E, because you can see that we can identify, we already can see what 1/2 m x dot squared is. It is just the kinetic energy of the particle, and v of x is the potential energy of the particle, which is the reason I call v of x the potential. So this portion is the kinetic energy and this portion is the potential energy, and this E now has the significance of total energy. So you can now see that whenever you have a conservative force, this equation, Newton's second law written down for this conservative force, leads to this, and conversely from here you can go back to that by differentiating. Okay. So these two are completely equivalent to each other in some sense. So I from now on take it that if you are able to write down the total energy of a system in this form, of a particle moving on the in one dimension in this form, then I take it that it is equivalent to writing this equation of motion, and vice versa in both cases. Now how do you determine the value of this constant? It depends on the initial conditions. You have to tell me what is the initial value of the position and the initial value of the velocity x dot, because this is a second order equation in time. Therefore you have to tell me two initial conditions, and once you tell me that, I plug those in here, and then this remains the same at all times. Even when x becomes a function of t, it has the same numerical value that it had at t equal to 0. So that is what is meant by saying it is a constant of the motion. Okay. So once we accept this is so, the next question is what sort of v of x can we look at and solve for? Well, the most trivial case is if v of x is a constant. Then of course there is no force, because if v of x, the potential is a constant, the derivative of the potential with respect to x is 0, and therefore the force is identically 0. So that is a very trivial case. The next non-trivial case would be to say that f of x or v of x equal to constant implies no f of x, or rather f of x identically 0. The next case would be when v of x is proportional to x itself. The potential is proportional to x. That is the first thing you can think of. The function is not a constant but is linear in the variable x. For example, v of x could be equal to mgx, where x is greater than or equal to 0. This would correspond to saying that the particle is moving in a gravitational field, constant acceleration due to gravity being minus g, and the positive x direction being taken to be the vertical direction from, say, the floor level. Okay. So that would be, instead of writing mgh, I have written mgx, but it is just a change of variable. So this would correspond to motion in a constant force field. This of course would immediately imply that f of x minus mg. The derivative with a minus sign, so it decreases x this force. That too we have studied. We know how motion occurs under a constant force field. The acceleration is constant and therefore the particle moves such that its displacement at any given time t is proportional to t squared in the leading term. The next in order of complication would be when v of x is a quadratic function. So what happens if v of x is proportional to x squared? So let us write it as constant times x squared, and for reasons which will become clear in a minute, it is easier if you write half times the constant times x squared, where k is a constant, k equal to positive constant. What happens now? The force f of x equal to minus kx, because it is the derivative with a minus sign, and now you see the reason for my putting a half here, because it cancels the 2 here and it makes the algebra a little simpler to write down. Okay. What happens now is that the equation of motion becomes x double dot equal to minus k over m x. Now what are the physical dimensions of this quantity k? As you can see from here, the physical dimensions of k over m, this has got dimension length and that is length, and the second derivative puts a 1 over t squared here. Therefore the physical dimensions of k over m must be t to the minus 2. It has got to be 1 over the second squared in units, right? Or square root of k over m, physical dimensions equal to 1 over t, which has got the physical dimensions of a frequency. So we see how a frequency is emerging here, how periodic motion is emerging from this equation of motion. This quantity here has the dimension of the square of a frequency, and k is positive, m is positive. So let us write this as equal to minus omega squared x, where we have identified omega to be equal to square root of k over m. Square to remind myself of the fact that this is a positive quantity here. Okay. So once I have this equation, and this is the equation of simple harmonic motion, this equation defines simple harmonic motion. Let us call it SHM equation. The next task is to ask what are the solutions of this equation here, and to see explicitly that it is a periodic solution. But even before that, we begin to see something else. I have said that once you have an equation of this kind, one has an identification with a constant of the motion of this kind. So let us go back to that language and ask, what does it say now? What does this equation say? This thing will imply that the following quantity, 1/2 mx dot squared plus 1/2 kx squared equal to E, and this is the total energy. So as soon as you have this equation, or you have a quadratic potential, a potential proportional to x squared, you have the statement that 1/2 m times the velocity squared, this kinetic energy, plus this potential energy is a constant, and the potential energy has the shape of a parabola because it is 1/2 x squared. In fact, if you plot it, it is very simple. If you plot this potential as a function of x, you have v of x. It is a parabola that passes through the origin in this fashion, and this is 1/2 kx squared with a single minimum at the origin here. And now you can see what is going to happen even without solving the equation of motion. First of all, E cannot be negative because it is the sum of two squares here, and m and k are positive constants. So E has some value like this, for instance, and this is a constant. For a given initial condition, the total energy is given some positive value. it's a constant. Then this particle cannot be in this region at all, because if it were in this region, that's the potential V of x at that level, and the total energy is this much, therefore this must be the kinetic energy with a minus sign, but the kinetic energy cannot be negative. So it immediately says that if the total energy of this system, of this particle, is some given number E, then the particle cannot go to the right of that point or to the left of this point. It's restricted to this region about the origin. And what it actually does is to oscillate back and forth between this point and this point, such that its total energy remains constant, but when it comes here, it's clear that all its energy is potential, because the potential energy is equal to the total energy here, and when it goes there, all its energy is potential, zero kinetic energy, but it has kinetic energy here because the potential energy is 0 and the kinetic energy is a maximum here. So the kinetic and potential energies of this particle are oscillating back and forth such that the sum is constant, and the question is, what's the frequency of oscillation? And the frequency is obviously omega, or at least the angular frequency is omega, because it immediately follows from this equation. We can solve that equation and write the solution. The general solution of x double dot equal to minus omega squared x is x of t equal to, there must be two constants of integration in this problem, because you are integrating a second order differential equation. So let us call those constants a and b. Then actually one can solve these equations by inspection, because we know that if you differentiate sine omega t, you get cos omega t with the factor omega. You differentiate it again, you get minus sine omega t. So we know that both sine omega t and cos omega t have second derivatives which are themselves times some constant, and therefore they are solutions. So the general solution is of the form a cos, let me call it cos here, a cos omega t plus b sine omega t, where a and b are constants, arbitrary constants. In other words, independent of t and x, of course. Okay. How do you find these constants? You have to tell me the initial conditions. You have to tell me what is x of 0 and what is x dot of 0. For instance, if you started at this point and let go, then the particle will start moving backwards towards the origin, because the slope of v is positive here. So v of x has a positive slope, therefore minus dv over dx is negative, and negative force means it points towards the origin, backwards from wherever you are. It tends to decrease x. So the force restores you to this point here, but it overshoots because of conservation of energy till it comes here, and here the slope is positive. In this case the slope is negative, and therefore minus the slope is positive, which means the force is directed to the right, and therefore it moves back in this fashion. And indeed you see that cos and sine are periodic functions with a time period which is 2 pi over omega. So you can write this in many ways, but here is one way of writing it. There is an equivalent way of writing it, or there always has to be two constants of integration. So you could also write this as a cosine or sine, it does not matter, depends on how you choose your constants, omega t plus some delta, or b sine omega t plus some other delta prime. These are all equivalent ways of writing the same solution, because you could also write this as a cos omega t cos delta, and then sine omega t sine delta. So you can identify a sine delta and a cos delta with these constants. Well, let us not even use the same symbol here, something else, say c or d. They are all equivalent ways of writing exactly the same solution. There is one more way of writing it using complex numbers. What would that be? We know that cos omega t plus I sin omega t is e to the power I omega t. So you could also write this as equal to some constant C1 e to the I omega t plus C2 e to the minus I omega t. That is yet another way of writing exactly the same solution. Okay. But there are advantages to writing this solution in this exponential form, because the derivative of an exponential is again the same exponential apart from a constant. The disadvantage is that since x is a real number, it is a real displacement in this problem, the complex constants, the constant C1 and C2 will have to have imaginary parts. They will have to be complex so that the final x of t is real in this case. So this is a completely real representation, but this is a complex representation of the same solution, it does not matter. Okay. But we have a general solution and these solutions are periodic. So now we have our first important result. We can also write cos omega t or sin omega t could also be written as cos 2 pi nu t which is the same as writing cos 2 pi t over capital T, because this is the frequency, this quantity is the frequency, this quantity is the time period, this quantity is sometimes called the angular frequency. But as far as we are concerned, they are all very, very simply related to each other. We have omega equal to 2 pi nu equal to 2 pi over t, okay, explicitly. I am going to use loose terminology, this which is what is done in physics very often, and just call omega the frequency. It should really be called the angular frequency, but I will call it the frequency because it is related to the time period as 2 pi over t is omega, or t is 2 pi over omega. Okay. So the motion is periodic, the solutions are periodic as we see, and the time period is 2 pi over omega, and the crucial question is what is this omega? And now comes the point. The moment I have any dynamical variable, any variable at all, we saw this in the example of a particle moving under the action of this potential, but if you have any dynamical variable u such that the total energy of the system which is described by this variable u has the form some alpha times, if the total energy has the form alpha times u dot squared plus beta times u squared, if the total energy has this form, that it is some quote unquote kinetic energy which is dependent on u dot squared and a potential energy which is dependent on u squared with some positive constants alpha and beta. So if this happens, then u exhibits simple harmonic motion. That is guaranteed by the same argument that we went through here. It does not matter what this u is. It could be the displacement of a mass which is attached to a spring, it could be the angular displacement of a simple pendulum, it could be the level of water in a u-tube which is going up and down in each arm in simple harmonic motion, it could be the charge on a capacitor in an electrical circuit, and so on. There are lots and lots of instances where you have simple harmonic motion. We will see some of these things as we go along. I will give some physical examples, but all that we need to do is to identify the total energy to be of this form, and the job is done with frequency, and this is crucial, with angular frequency, of course, with angular omega equal to the ratio of these coefficients with a square root, and that is it. In the simple harmonic oscillator case which we looked at, the particle, this quantity was 1/2 k and this quantity was 1/2 m. and then the square root of k over m was your frequency, and now it is the square root of beta over alpha, that is it. So this is all you have to do. In any physical problem, if you want to find out if the motion is simple harmonic, write down the expression for the total energy by whatever physical argument, and if it turns out to have the sum of these two squares with positive coefficients, you are guaranteed that the dynamical variable whose energy is given by this expression will vary simple harmonically with time, periodically with sines and cosines as the functions, with an angular frequency which is the square root of this ratio here. There is another way of seeing this and asking what is the total energy. Well, this example tells us what it is. For instance, this point here for a given energy is the amplitude. So let us call that A and this minus A in this fashion. Then it is immediately clear that the total energy of the system is equal to the potential energy at the point A. So it is immediately clear that E equal to 1/2 k A squared in this problem, where A is the amplitude. So we also have another feature of simple harmonic motion, namely that the energy is proportional to the square of the amplitude in this form, and that specifying either the energy or the amplitude is completely equivalent. Once you tell me what the constant k is, you could either tell me the energy or the amplitude. If you tell me the amplitude, I tell you the energy, and vice versa. That is the end of it. So this is another important feature of simple harmonic motion, a very obvious one. But the most crucial feature of all is the fact that this time period does not depend on the amplitude at all. The amplitude is determined by the total energy or vice versa, but t is independent of that. T equal to 2 pi over omega, independent of E. I can't emphasize this strongly enough, because this periodic motion, which is called simple harmonic motion, has this defining property, this very crucial property, that the time period of this motion, periodic motion, is independent of the energy of the system altogether, or independent of the amplitude of the system. And the next thing we will do is to look at physical examples, several physical examples of simple harmonic motion, and you will see this feature emerging and what it implies.